The hypergeometric distribution is a stochastic process whose repeated experiments are not independent. So this is just where we do the choosing. You're right? This is just where we're doing choosing, that's all. This is what we did in the last unit. We're using combinations. So there's nothing really new here. Now this formula looks really complicated. A is the number of successful outcomes. B is the number of failure outcomes. N is the number of trials. And X is what we're trying to get. And you've been using this formula all along, right? Wherever we did probability using choosing. Tabulate and graph the probability for the number of spades dealt from a well-shuffled deck of cards if 3 cards are dealt. Okay, so you know in a deck of cards there's 13 spades and 39 non-spades. In other words, hearts, clubs, and diamonds, right? That's a 3. All right. So what we're counting is spades, so let X be the number of spades okay, so X is the number of spades and we'll do the probability of X. So we either can have, when you're dealing 3 cards, you can either have 0 spades, 1 spade, 2 spades, or 3 spades. So that means we'll have 13 choose 0, and out of the 39 non-spades, we're going to choose 3, and we're going to divide that by 52 cards in a deck of cards, 52 choose 3. And this is approximately 0.414. 1 spade, 13 choose 1. I hope you can see that. Okay, I'll just try to. This is 39 choose 2, 52 choose 3, and that is approximately 0.436. 13 choose 2, 39 choose 1, divided by 52 choose 3, and that's approximately 0.138. 13 choose 3, 39 choose 0, 52 choose 3 is about 0.013. Well, how many spades can you expect to have? Well, before I show you the formula, you can know that this is the probability distribution for hypergeometric. It's an example. Expected value of the number of spades is going to equal 0 times 0.414 plus, plus 1 times 0.436 plus 2 times 0.138 plus 3 times 0.013, and that is about 0.436 plus 2 times 0.138 plus 3 times 0.013, 0.751. You can expect, assuming I did that right, you can expect 0.751 spades when dealing 3 cards. On average. Okay, so there is a formula, and that makes your life easier. And the formula is, I'm going to write it up here. Expected value of x equals NA over A plus B. So there are 52 cards, so A is the number of successes, and in this case there's 13 spades. B is the number of failures, 39. I'm sorry. So A is the number of spades, they're the number of your successes. B is the number of non-spades, 39. We have 3 trials, and it's times 13 again, which is the number of successful outcomes. So it's going to be 3 times 13 divided by 52. Oh, we get 0.5. I must have done something wrong here. Maybe it's 13 times 3, 9 NCR2 divided by 52 NCR3. No, this one seems right. We'll have to look at that. Pardon? This one here? Oh, did I? Oh, hold it. Okay, so 3 times 13 is 39, right? Divided by 52. Oh, it's I got 0.75 on this one. So it might be a rounding issue, because here I rounded to 3 decimal places. Yeah, so this is a rounding issue here. Okay. Anyway, I was just illustrating the formula. So it's just a shortcut method of finding expected value. Okay. A hat contains 20 names, 12 of which are female. If 5 managers are drawn from the hat, what is the probability there are at least 2 female? So you have 12 females and you have 8 males for a total of 20. Guess they're watching movies next door. Sure. Did you need the previous question? You just wanted that stuff, right? I'm just looking for it. All right. What is the probability there's at least 2 female? So let X be the number of females. Okay. So the probability X is greater than or equal to 2. If 5 names are drawn, so we want the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. That's a lot of work, so let's just go 1 minus the probability of 0 minus the probability of 1. Okay, so we're going to go 1 minus 12 choose 0 times 8 choose 5 over 20 choose 5 minus 12 choose 1, 8 choose 4 over 20 choose 5. And when you work that out, that will be approximately 0.9422. So very high probability. What is the probability that a bridge hand of 13 cards contains 6 spades, 4 hearts, 2 diamonds, and 1 club? Let S, can't forget S, H, D, and C represent the number of spades, hearts, diamonds, and clubs respectively. Okay, so we want the probability S equals 6, H equals 4, D equals 2. Uh-oh. A little bit too quick on the closed bracket. And C equals 1. So that's going to be, well, we know there's 13 spades in a deck of cards, so we want to choose 6 of those. There are 13 hearts, and we want to choose 4 of those. There are 13 diamonds, we want 2 of those. 13 clubs, we want 1 of those. All over 52, choose 13, and that is approximately 0.002. I'll put that up a little bit higher so you can see. Okay, there's the expected value formula again. Just know A equals number of successes. B equals number of failures. N equals number of trials. A box of thumbtacks contains 15 red and 20. We did this before. You can just ignore that for now. Just keep it simple. You can either calculate the sum of the probability of XPX like I did before in example 1, or you can use the formula, which I think is easier. A box of thumbtacks contains 15 red and blue tacks. If 10 tacks are withdrawn at random from the box, what is the expected number of red tacks? So we'll let R equal number of red tacks how do we spell tacks? Tacks. Let B equal number of blue tacks, and N is number of trials. So I think you can see that R equals 15, B equals 20, and the number of trials is 10, right? Because 10 tacks are being withdrawn. So the expected value of the red tacks is going to be NR over R plus B. So the number of trials is 10. The number of red tacks is 15. All over number of red tacks plus number of blue tacks. And this is about 4.3. So on average, we can expect to draw 4.3 red tacks when drawing 10 tacks. Now, most textbooks teach this question using this formula, but I want you to ignore it because it seems like an overcomplicated way of doing a very simple exercise. To answer this type of question, which I will read in a second, is just use proportions and equate them. 1,000 fish in one of the lakes were caught and tagged by the Department of Fisheries. After a while, a new catch of 500 fish was caught, and it was found 60 had tags. What conclusions can be made concerning the number of population in the fish? So let X be the number of fish in the lake. I'm not doing very good in my spelling today. There we go. In the lake. Okay, 1,000 fish, and so the total population of fish divided by the total number of fish that were tagged is equal to the total in our sample space over, they got a new catch of 500, and out of those 500, only 60 were tagged. So you have population of the lake over total number of fish tagged in the lake, sample size over fish tagged in the sample size. So if you were to work that out, you would get X is approximately equal to 8333. There are about 8333 fish in the lake. Can I explain anything better? That's a good question. I've never used it, so it's sort of, that's something I can look up for you if you really want to know. We can just Google it. Okay. Actually, I think I have a textbook that uses that method. I'll show you. But this is easier. Why not use easy? Okay, good.